Hello, welcome to Mr. Perrin's first video on kinematics. Welcome to Illinois, or at least my very badly drawn rendition of Illinois. We've got some key kind of points on here. We've got the state border in black, some various important towns in red, and we have the major highways in blue. Now, to be perfectly clear, not everything up here is entirely relevant, but it is useful for giving us a sense of scale. What we're going to do is we're going to take this black marker and draw a single dot. We're going to draw this dot in right here. Do it nice and big so everyone can see it. It's kind of in the middle of nowhere. Nothing really going on there particularly, but it's very useful for our set of directions. Now, from here, you're at a crossroads of Illinois. You can go north to Rockford, south to Bloomington, west to Moline, or east towards Joliet and eventually Chicago. Imagine you and your friend both start there, at this black dot in the middle of nowhere. And you each take off. You're traveling at 70 miles per hour, your friend's traveling at 90. Who makes it to Chicago first? Well, the instinctive response is, oh, the person who's going faster. But what if your friend's going this way at 90 miles per hour, and you're going this way at 70 miles per hour? That difference in direction is one of the key ideas we need to start talking about in physics. Because while 90 miles per hour is faster than 70, if you're not going in the right direction, or if you don't account for the direction you're traveling in, it ultimately doesn't matter. This idea, this concept, is what we call a vector. A vector is not only a number, it is the direction the number travels in. So we can use this to talk about how far something travels, how fast something is going, how much it's speeding up or slowing down. All of these we can talk about with vectors, and we'll talk about them a lot throughout the year. This analogy is just a place to start. So let's clean this off and take a look at each of these ideas on the smaller scale. Where we'll start is talking about how far you travel. Okay? So let's say you start here. This is your starting position, or I'm going to call it position 1 or position 0, but this is your starting position. Position is a measurement of where you or an object is. And from this starting position, you want to go to your ending position. Okay? Now, there's two ways to measure this. First is, how do you travel? Well, if you go down to right 5, up 6, over another 10, down 5, over another 4, and then up 1, your distance, which is directly the path you traveled, is 2 plus 5 plus 6 plus 10 plus 5 plus 4 plus 1, or 7, 13, 23, 28, 32, 33. So your distance is dependent on the path you took. It doesn't have a direction, it's just a sum of all the steps. In this case, 33 something, let's call it meters. Assuming all these are meters. If they're all miles, it'd be miles. If it was all centimeters, it'd be centimeters. On the other hand, we have displacement. Displacement is the straight line path from start to finish. It only cares about how far did you go as a result. In this case, it's 19 meters to the right because that is the straight line distance between them. To put it another way, if I started here and you closed your eyes, don't actually close your eyes, but for sake of argument, pretend you do. And then I ran out of frame over this way. And I ran around the room that you can't see, and then I came back into frame running this way. And out of frame again, and then I came back in frame and ended here. And then you opened your eyes. You don't know or care or really have any way to measure how far I ran around. What you do know is that I started here, I ended here. This is a good way to think about displacement. Whatever happened in the middle, we don't care about. We care about the start, we care about the end. That's it. Displacement is often referred to as the change in position, or your delta x. The variable x is position in physics almost universally, whereas even when we're not moving necessarily in the next direction. Why? Because physicists and scientists hate high school students. Alternatively, it's just convention at this point. So x is your position. Delta is change. Whenever you see delta, you're talking about change. Changing your y values, change in your bank account, change in position. Delta will always be, always, the final minus initial. So let's say, for instance, the starting position is 3. The ending position is 22. If you start here and end here, your displacement will be 22 minus 3, which is 19. 19 meters to the right, or 19 meters positive. But let's say we flip that. What if you started over there where I labeled the end, and ended over here where I labeled the start? Let's go from, let's just flip that. You start here and here. Start to end. Final minus initial. In this case, it would be 3 minus 22, which does give us negative 19. And in this particular case, we went from right to left. We traveled to the left.
In the future, we'll talk about how we can use negative as a shorthand, but for right now, just understand that you can have negative numbers.
Distance versus displacement. Okay? Next, we'll talk about how fast. Before we get into this, go back to the original description I gave you with the map of Illinois. We talk about speed. We look at our speedometer. We have a speedometer in a car. It tells us how fast we're going. A speed is how fast we're going, but unless we know a direction, especially in this class, it's not useful. It doesn't tell us anything meaningful. Where speed is just a number. It's a number you can read off your dash. Velocity is how fast and what direction. Let's go ahead and put those definitions on the board. So not only do we have how fast an object travels, we can get to these a little differently. One of the first kind of equations that we deal with, one of the first equations that you've already dealt with, whether you've realized it, is how speed and velocity are defined. So your speed is equal to your change in distance over your change in time. A more shorthand way to say this will be delta D over delta T. This, strictly speaking, is for your average speed. If your speed isn't changing at any point, if your speed's constant, if it's always 60 miles per hour, your average will be the same as your actual. Your velocity, on the other hand, is defined as your change in position or your displacement over your change in time. When we abbreviate this, what we will see is a couple things. First and foremost, the expression will typically look like this. But what you will often see is an average or the such. When we shortcut averages, it's done by writing a bar on the top. This bar over the top here means average. Again, velocity will have a direction. So let's go ahead and take a look at this up here, in terms of speed and velocity, and do it slightly separately. And we'll start with speed. We already said that the distance it travels is just all the parts added together. So 2, 5, 6, 10, 5, 4, 1, 7, 13, 23, 28, 32, 33. So your change in distance, or the distance you travel, in this particular problem up here is 33 meters. But how long did it take? Well, we don't know. How long does it take you to go 30 meters? Well, it's about the length from the front to back of the classroom. I walked mine earlier. It takes me about 12 seconds. So we're going to say t, or delta t, equals 12. Typically, this will either be given to you on the equation, or I'll give it to you on the sheet of paper, or you'll find it experimentally from your data, like you will later today. Once you've got this, once you've plugged it into this very early formula, then you need to simplify. What's 33 divided by 12? And you get 2.75 meters over a second is just meters per second. And because this is a speed, it doesn't matter what direction you're going. This is an average. So on average, mapping following this path, they're traveling 2.75 meters per second, which is about 3 steps per second for the average person. If you're taller, less steps. If you're shorter, more steps. On the other hand, we have our velocity. Our velocity is our change in position, or our displacement over time. The time hasn't changed. It is still at 12 seconds I measured earlier, but the displacement is not the 33. It's this 19 we measured to the right. So again, there we go. Once you've done that, again, it's just divide. In this case, it's 19 divided by 12, which is 1.58. And we need to designate a direction because this direction matters to the right. Speed, velocity. These are separate but similar ideas. Please make sure you're using the proper terms and understanding. If I ask for a velocity, make sure you're giving me a direction. If I'm asking for a speed, you don't need to give me direction, but I'll take it if you happen to give it to me. Similar but different. Let's take a look at a kind of sample problem, and then we'll bring it all back and summarize everything all together. So for this practice problem, you've been sent on a grocery run. You start from home, you run over to Walmart, and you pick up the things there. At the end of your run to Walmart, you realize that they're missing something. I don't know, milk, eggs, Reese's peanut butter cups, something. So you then have to drive the 7 miles from Walmart to Jewel to finish your grocery run, pick up the last supplies you need. After that, you drive straight home from Jewel to home, another 10 miles at the end of it. You have 4 questions you need to answer. Number 1, what's the distance you traveled? Number 2, what's the displacement? Number 3, if all this takes you an hour, what's your speed? Number 4, if all this takes an hour,
what's your velocity?
Go ahead, give it a try, pause after I'm finished talking, and then check back when you're done. Okay, if you went through and did the math, distance again is just the total amount you covered. Doesn't matter how the path is. Just you went 5, then 7, then 10 miles. That's 22 miles total. Your speed is your distance divided by time. 22 divided by 1 hour gives you 22 miles per hour. On the displacement side, it's all about the net result. All what happens if I look away and then look back. I start here, I end here. And in fact, I haven't moved. My displacement is 0. If your parents or your friends weren't around when you left and then you came back, they have no idea that you left at all, except for maybe the food in the fridge. But just looking, they don't see it. So your displacement is 0. 0 divided by anything is still 0. You'll note that there's no direction on this because 0 with the direction doesn't make sense. If you want to be strictly accurate, it's the 0 vector, which means it's 0 with no direction. The moment you have a step, you have to care about it. But if you're not moving at all, you're just not moving. This one was a little tricky, probably a little too easy. We're going to put up one more, and then we're going to answer it, and we'll be done. All right, so here we have a football field. Alex and Charlie, Alex in red, Charlie in blue, are running around the football field. They start here at this black spot, and they go to here. Charlie goes in a straight line from start to finish, where Alex runs around the field this way. The distances of the field are on the board. It is 48.8 meters wide, 91.44 meters this way, with the directions as lined out. This is the same directions that the football field at Richmond Burton go. With that said, here's what I want to know. For Alex, what is the distance, the displacement, what's the speed, velocity? And then I want to know the same things for Charlie. Please note the times are on the board. It is 12.1 for Charlie, 29.5 for Alex. Seconds, both. Go ahead, do the calculations. But before you do the calculations, think to yourself, which one has the greater distance? Which one has the greater displacement? Which one's going to have the greater speed? Which one's going to have the greater velocity? Think about this to yourself. Give it a try. Pause now. Okay, start to top. So Alex's distance space to pass, so they go 48.8 down, 91.44 over, 48.8 back up, gives me a total distance of 189.04 meters. Their speed is based on distance divided by time, so 89.04 divided by 29.5 is 6.41. Their displacement's a little harder. You got to think about this one really for a bit. They start here, they end here, so their displacement in essence is just one length of the field, the same as what Charlie ends up doing. So it's just one length of the field, which is the 91.44. And they're heading south according to our compass. We need a direction because we're talking about displacement. So 91.44 meters south, which means their velocity is 91.44 divided by the 29.5 seconds it took them to get there, which is 3.09 meters per second. Again, south, they're heading south on average. If you blinked or weren't paying attention, it looked like they moved over there roughly in a straight line, or at least that's what you'd guess. Charlie, on the other hand, has a distance of 91.4. They only go to one side of the field. Their speed is 91.44 divided by the 12.1. Gives me the 7.56 meters per second. And their delta x, their change of position, is also 91.44. Notice how if you're moving in a straight line, your distance and displacement are the same, minus the difference of having a direction. If you don't move in a straight line, or you double back on yourself at any point, your displacement and your distance are going to be different. This is a very useful kind of idea. In some small cases, we can use them interchangeably, but only in those scenarios. The velocity is the same as the speed. Again, same logic there. Because the distance and the displacement are the same number, the speed and the velocity are going to be the same number. But that's only because they're moving in a single straight line. To summarize, we have two different types of ways of measuring things. We have just numbers, speed,
Distance.
which are called scalars. They only give you, they don't tell you which way they're going. 70 miles per hour towards Chicago is a lot different than 70 miles per hour south. Next, we have displacement and velocity. These are numbers with direction. These are what we call vectors. Because they act in a direction. And we know what that direction is based on south, positive, up, down, some direction. Scalars, vectors. The scalar value will always be equal to or larger than the vector value because the shortest way between 2 points is a straight line. The vector only cares about the straight line path. Or another way to put that, the vector will always be equal to or less than the scalar value because all it cares about is the straight line. In this particular instance, if we look between these 2 points, Alex took a non-straight line path. You can see the distance they ran. Charlie took a straight line path, and thus they're more akin to just the displacement. We could measure it as distance, but the path they took is also the path of displacement, which is why they're one and the same here. Again, this number will always be bigger than or equal to this number. This number will always be bigger than or equal to this number. Bigger, equal. And there we have it. That's the difference between distance and displacement. Thank you for watching, and have a good day.